So I have my name is Alex Foessel, and I have this either privilege or curse of moderating this panel that includes two people. One of them is John Reid. He was my boss at John Deere for most of my time there. The second is Red Whittaker, who was my advisor at Carnegie Mellon. So once again, I'm not sure whether this is a good place to be or a really bad place to be. In any case, what I would like to do today is to start discussing the topic of robotics and outdoor autonomy in the context of industry. And I'm going to go through a few slides to really set the stage, and I'm going to focus on the aspects of commercialization. We have talked about academy and development of technology and building products, right? But in some cases, in some industries, we're getting to the next stage where some of us are thinking that there's good money to be made by commercializing robots in markets that care. Some of you were here when a couple of weeks ago we brought a number of very large agricultural companies from Brazil. They came to look for technology because they can't wait anymore to solve and automate the very large number of tractors, thousands, in their operations. In any case, let me get to some topics here. And these are going to be inspired in agriculture, but once again, this panel is about industry. So these are also valid for construction, and we saw some of mining, etc. But the key thing that we have in front of us is that academia is focusing on showing the art of the possible, and it moves the ball every time. And there's a lot more to do. But companies are focused on making money sustainably. So that's the focus on business cases and trying to understand how money is going to be made. In the case of agriculture, for example, it has been gathering data, and good data, since the integration of GPS on machines. So now what was something that was just an account of a few people about how a crop a season went, now is actual data, is coherent data, geoposition and with time. The topic of safety, I think maybe, Pete, you said, it's not about just being careful. It's about very structured, functional safety and safety on the intended function standards, and those are emerging. And then the other piece is the broadening the focus, not just on the functionality, but as we're going to see, on the complete task and also aspects such as the life cycle. And the question about Marshall, your question, what is there for academia to do? A ton. There's a lot more to do, and we're going to get to that. So about data, why is this important? It's because data is not only important to actually develop trusted technology in terms of automation, but also because the data is going to be critical for your business case. It doesn't help to suggest that you can save some labor or apply fertilizers in a little bit better way if you don't have the data to back it up. So this is something that has been happening for the last 20 years, and the amount of area and data quality is very, very good to make the business case and also to run statistical models to understand how you can improve agricultural operations. And this data gathering is just increasing in terms of speed. So that brings us to how is farming and agriculture managed? Same with mining, same with construction. It's not anymore based on only a few people who are knowledgeable. More and more is managed by systems that analyze the data and with an industrial factory mentality are always working on continuous improvement and driving more productivity, more safety, more quality, and of course cost reduction. So for example, when we look into what's the money that goes into a farm, and this is a very generic pie chart, you're going to see that labor is about 10%. So labor displacement is not really the main business for automation in agriculture. It's really to reducing the inputs, reducing the fertilizers, the seed input, the chemicals. And bringing robotics into agriculture is really about understanding that it's a production system. same as in a factory. So for that, understanding what are the stages and where automation makes the most business sense is critical. So for example, here we have a tractor that is plowing, autonomous tractor. That's great, but that is just table stakes. That's the entry point. Because really, and John, thank you for this slide. I told you ahead that I was going to steal it. But really, many a times, those of us working in the functionality focused on that orange step, which is the actual plowing. But a farmer needs to set up, plan, maybe he's planning from the previous year, he's setting all of the resources, he is adjusting things, integrating things, bringing the stuff to the field, and then at the end of the job, there's also a number of tasks. So for whoever is able to actually automate in the context of all of these tasks will drive the adoption. Also, no one really, who said something about that going from A to B is not really the business case. The business case has to do with the job, and in the case of agriculture, it's an agronomic job. A tractor by itself does nothing, and a robot by itself does nothing. But if you have the smart implements that are going to drive the actual activity and the engagement with the ground or the planting or the harvesting, that's where you create value. And furthermore, when you think of the life cycle of the customer, you have the sales part, and there's a lot of effort into creating a product that customers would buy, but the customers will make the money using that technology over multiple seasons. And that goes back to the business case. Because at the end of the day, when someone buys a tractor or let's say, an automated vehicle to do some job, the only thing that they have gotten when they buy it is a hole in their checking account for the amount of money they paid. They haven't gotten any value yet. And hopefully over multiple seasons, that value is going to come. I couldn't finish this talk without at least addressing safety. This is the announcement of a conference that happened last year. It happens every year from the Association of Equipment Manufacturers. This is the industry getting together to understand product safety. And many of the tasks, the talks are about autonomy. And for example, trying to understand that industry cannot just go to automotive and say, oh, you sold it for automotive, so we're going to just bring it in. Because you would bring a lot of cost that you don't need because the risk profile is very different. In highways, you have many vehicles, you have a lot of risk. If an accident could cause much loss of life. Instead, most of the time in farming, you have an area that is dedicated to that particular task. So everyone who is actually going to a field knows what they have to do, and they're working in coordination. So once again, there are multiple dimensions of risk, but certainly, for the most part, agriculture and other field operations present a more manageable element of risk. But at the same time, crops are different, the weather is different, fields are different, and the globe is very, very diverse in agricultural operations. So there's another side of complexity. You talk about SOTIF and functional safety. So some of us are putting a lot of effort and money to create dedicated safety cases for agricultural automation. I'm not going to go into the details, but of course some of this is inspired in automotive, but adapted correctly to agriculture. Finally, the topic of simulation is key, and for some of us, getting to the level of fidelity of outdoor automation is really important to test all of these technologies. So I'm going to thank everyone who is working on simulation for DoD, because to some extent it's outdoor, it's all-terrain, and that works for agriculture and construction. Finally, this is just getting some new machine forms. It's not just about tractors being automated or sprayers being automated or trucks being automated. Also, it's about, well, what if we have a solar-powered robot that can run every day without any maintenance, without any tendering, without any fueling? So this is one example of technology that is being deployed commercially by the hundreds in Canada, the US, and Brazil. With that, I'm going to stop talking because the most interesting part comes with John Reid, and then after that, Red. Thank you.
Good morning, and thank you for the opportunity to be here today. Actually, I am not a CMU alum, but you've seen me around a lot because started in the 90s, being invited to be on Mark Ollis's PhD thesis committee, and that was actually a really great day because they were celebrating a lot of the teams that had done projects over the summer, I think, and I got to see coins being handed out by Red and others. And then after that, shortly after that, I left and went to John Deere, and so to kind of lead field robotics activities taking place there inside of Deere. And NREC and CMU were partners with us all along the way. I think even until today, I believe NREC still has some work with John Deere. And then I have one more experience. After I left John Deere, I went to Brunswick and worked in recreational marine for a couple of years. And in a very short period of time, working with CRL, delivered autonomous docking that is going towards production right now. So it's really interesting to see how a smaller industry can move faster when a technology stack is there and available. I'm going to talk about agriculture a bit more, and as Alex kind of set this up very nicely, and during my time at Deere, there were a lot of different vehicles and attempts and activities to provide solutions that were based on autonomy. And Stuart Moorhead, who's here, he actually put this slide together many years ago. And this is just an example of all of them. And, in agriculture, all of these activities were kind of based on the idea of trying to create a production outcome in a driverless way. One or two of these is connected to products that have made the market. Actually, one of them made the market. Alex led it. And it's even off the market with John Deere today. So, some of these things don't necessarily have longevity and in some parts of the industry. Okay, so what I really like about the application of field robotics to agriculture, though, is that it actually has applications in precision agriculture, too, and in fact benefits from a lot of the things that have happened in precision agriculture. With GPS technology, it creates a platform that enabled a lot of incremental steps to take place that lead to a wave of autonomy that's starting to happen in the industry today. In fact, you kind of look back and think how far we've moved from the 90s, where machines, you had to customize everything in order to do steering or brakes or anything. And a lot of that is automation's taken place. You have a software-defined machines today. And in the platforms we have to work with in the high end of the industry have high-fidelity location, we have connectivity and telematics, cloud-based data services, and electrification is giving the ability to actuate parts of the machine. You probably never see battery electric, but certainly having electrification for actuation really is an enabler for a lot of the automation that's taking place. And AI has actually moved into these systems as well all along this journey. We have, starting with, my PhD work in the 80s was vision guidance using a PDP-11 strapped to the top of a tractor and using it with a very, very, somebody talked about the low pixel count, and I think we just had a 4-bit pixels with, gray levels that, essentially was being used for guiding a tractor down row crops. That's commercialized and on the market today. Also, things like path planning and controlling the mission, even when an operator is on board, are things that are available, not fully autonomous, but it really has enabled the productivity, being able to reduce the skill level of labor. Automation and autonomy and AI is augmenting human performance as well, and this is an NREC product that Deere has on the market, and it basically allows machines to work in close proximity, and you're managing the fill. You can just see the stress go out of the operator's face when he's driving the combine and working and not focusing on is he going to run into the machine system that's adjacent to him. And we're starting to see the wave of companies with trying to get the multiplication effect of human performance through autonomy, and I'll spend a little bit more time talking about that. And then I think it's really interesting to see the See and Spray, which is precision spraying that reduces chemical, but humans can't do that job on the implement. And it's opened the door that maybe there's levels of automation that still can engage the operator on the machine, but you're helping the machine do things that the human can't do at the speed that the machine is doing it, and all providing value for the farmers. Several people have mentioned this data side, and the journey we went on started with GPS, and data came in the last decade, being able to really leverage it. But frankly, if you could do it over again, data is the fuel that's driving a lot of this automation, because if we can measure it, we actually can see that opportunities to make things better, and the data also can be used to take some of the complexity out of the robotic systems that take place. And so it's really, many people have mentioned data, but I think it's actually opened the door for field robotics to really expand even further. So here's kind of an example of where the possible future state can go, because we kind of sit here wanting to do robotics, and just in our mind it's well, when will everything be roboticized in agriculture? And actually, I think there's going to be this mixed pathway along the journey. One pathway is keeping the human in the loop, but the machine is getting more and more intelligent with the robotics capabilities integrated into the machine beyond the driving, even assisted driving. But the human is there to kind of deal with the fact that there's a lot of uncertainty in agriculture, and safety in particular is a complicated task for all the different conditions around the world. But there's this other pathway that's thinking about the farming system and creating the job outcomes at the work site level. And in this type of world, the autonomy is enabling solutions that can be more fully automated. And in thinking in that work site context, there's a lot of job steps to be done too. And so I really believe both of these are playing out in production agriculture. And there's a lot of commonality between the technologies that are on both sides of this. So the other thing with the tech stack that's coming from precision agriculture is that it's also opened the door for transformation beyond this human-driven machine side that's been the predominant model in agriculture. And when we think about this, we're all kind of working and taking existing vehicles sometimes, retrofitting them like the big tractors to make them autonomous. But with all of this tech stack that's in place today, there's no reason why the machine form has to stay the same. In fact, it may be an opportunity to leverage these novel machine forms like Alex just showed in the slide that can achieve the job. It's a lower cost, it's maybe lighter, can operate day and night, and all of those types of benefits. And especially, in our mind, we have to get beyond the part of the business model being that the farmer is going to want to run these machines. Actually, the service models that were talked about earlier would apply to agriculture as well, and could open the door to really an acceleration of this transformation. And in fact, I think that helps deal with the complexity of the dealership Alex talked about. The dealer also has to have new skills to manage these machines, to keep them up to date. And so actually a service-based organization has more of an opportunity to deal with those challenges. And we see a lot with the scouting platforms on the small end. This is interesting. It's kind of introducing some new things like phenotyping, but little battery-operated machines that go over thousands of acres. There's got to be a lot of intelligence to manage the complexity to make it really easy for the farmer to use. So again, that's a good reason to have the data architecture. I think it's, though, not the solution for large-scale production agriculture and field robotics. It might work for greenhouses and things like that where you have a more limited environment. So, others have talked earlier about the challenges with perception, and it's always been kind of the big gap for agriculture. Lots of times trying to just take off-the-shelf technologies and leveraging and use them. But over time, there's been technologies that have emerged that help do some things. So I mentioned I did vision-based guidance in the 70s. It took John Deere till 2016 to get their version of this on the market, and as I understand, they were kind of risk averse about it being how big of a solution it would be. They sold out of all their production for that year in the first week, with farmers buying it for these large rig sprayers that they're trying to drive down through the fields at high speed. Active field control was the perception sensor using stereo that's monitoring the wagon and trying to understand how to position it relative to a combine so it can fill. And then actually more recently, situational awareness types of applications. These first two are kind of like doing a function and not really so much robotics, but taking those technologies and putting enough of these sensors around a tractor so that you can actually have an awareness of the environment so that it can be operated autonomously is really, it's doable today, and it actually combines the needs for autonomy with an ability to provide value, because these sensors also are telling the farmer something about the crop and the materials that are flowing into the machine that they can use to understand the agronomic impact of the technology. And I did mention this, the See and Spray is an interesting example. I talked about it being, doing things that a human would be challenged to do, but I think the other interesting part of this is that many times we're focusing so much on the tractoring or the driving of the machine that we really have not thought about this challenge in agriculture, where there's lots of implements that need to be automated as well. And in fact, one of the bigger challenges in agriculture is they often have the implement isn't made by the manufacturer of the tractor, and they have multiples that they put in there. And so we're starting to see a beginning of people thinking about more intelligent implements. I believe it's a space that's been not enough energy has been put into this, and it's going to be an enabler for future autonomous systems, because you have to have those implements. And I won't go over this slide, but this is one of the learnings that I had when you looked across those different applications that I showed earlier. The ones that tended to pencil out the best were the ones that were looked at a work site level, and you had to understand all of the job steps and how did labor is it displaced, or how is it utilized, and how do you get the entire job done. And it isn't just the video of running through the field doing the task, but there's a lot of stuff that's required to set that up. So it is important that we think about this. And while there's a lot of applications in agriculture, somebody asked what will we do next. Actually, I think with all the technology that's been developed, in agriculture, we're seeing only examples of one job step being automated today. And you think about all of these different steps that Alex had on his slide, we're going to have to do all of those eventually. And so there's lots of opportunities still. I like this slide, this paper. There's a paper references at the bottom from Thomas. But it was talking about this journey of automation to autonomy and its relationship to technology and other factors. And it's just kind of the takeaway message here is that we often get focused on, let's develop this technology, and here's the application that's going to be the successful application. This paper talks about a lot of companies that adopted automation, moving towards autonomy, and it actually was a combination of factors that were involved, and especially this business model side has to be brought in. And in agriculture, we often think the farmer is going to be the driver of these machines or using these autonomous machines. That may be the case, but it isn't the only model. So it's really pretty important that as technologists, we work in interdisciplinary teams that bring in this knowledge of customer needs and think about the business model and those types of things. And then the ecosystem side is, there's lots of new services that in agriculture that are going to be required as autonomous systems emerge to replace the traditional services. And so all of that is something that usually has to come into play for the complete system to be effective. So the really interesting thing with the business model is that I mentioned making machines more productive is one aspect, but the work side is another one. And I think this S-curves that I showed earlier are really kind of in two spaces. One is that my advanced vehicle solution, robotics or even just intelligent machine, works to help me get the job done. And so the farmer appreciates what it can do. Or if it's remotely managed and autonomous, my machine solution does the job for me in a way that helps me run my business. And both of those are in play today in agriculture. So in summary, precision ag has been successful over the last 30 years. Autonomy is really now just starting to, you see it, lots of different companies emerging that are taking this. It is still kind of at the beginning of its journey though, because they're doing individual job steps. And a lot of times a farmer is going to have to, we're going to have to figure out how do we get beyond that to multiple job steps being put together, and those will be the successful solutions for the future. It's more than just integration of technology development. It requires thinking about the ecosystem and the business model, and if you focus only on the technology, then you're limiting yourself to trying to understand these other things. There's broader system requirements that are really important. And then finally, autonomy creates opportunities to transform the business model for the off-road equipment industry. And getting these job outcomes consistently is going to be the most important part of this. And the industry, unfortunately, is still very embedded in their machine systems. But actually, the autonomy stack on top of that is opening the door for broader capabilities that go beyond just the machines. And finally, the intelligent implement side has been underserved, and I think it's an opportunity to accelerate autonomy by getting the implements that will work effectively once the machine is fully autonomous. If I can just, I'll just quickly everybody showed a video, but Stuart's here, and we did do a project with Deere and CMU with Chris Dima and others. I can't remember if Carl Wellington was on this project or not. He may have already moved on. But it was autonomous worksite management in an orchard, and this U.S. Sugar was the orchard down in Florida. They basically already had robotics all over their orange juice factories, and they wanted to know, why can't we have this in the field to get the same productivity? So this was a system where it was displacing drivers by having a kind of like a security guard manager running multiple machines. It was an example of where we put this in the hand of an operator. It had to be a special person hired for this job. And this was pre the communication infrastructure that we had today, so installing that infrastructure was really a critical part to make this problem successful. And the key points about this, about why this is valuable, is that one, with the human operators, they do what they do, but you don't actually know what they do until you have the data. And so one way to get improvements over them was to have the optimized path planning. You had to have technologies like perception and localization to detect obstacles. Turns out this was a dangerous application too, because you had to not go in the orchard 48 hours after spraying. So the driver, probably didn't care if they weren't sitting in the orchard and spraying these dangerous chemicals because they were safer. And then we could have one vehicle or multiple vehicles controlled by one operator. As you can see here, there's the kind of turning at the end of the row. Autonomously driving. You see a lot of sensors bolted onto this that can be much more better integrated today in terms of a clean appearance, but very, very capable at the time for the job it was doing. And here's a second tractor that's pulling a mower coming behind it. So we had extensive missions with this type of system, and this kind of is, I think, really important part of this is that this system still had a lot of problems. It had a lot of false positives. It would stop frequently. The supervisor had to look around the vehicle remotely through cameras and decide whether there was a real problem, and then reinitiate the mission. But despite that, this system performed 30% more productive than comparing it against the human operators that were operating these machines. So there's value there. They could reduce the amount of labor. It improved the job quality with a better job for the people to do, and it was more productive. And one of the reasons it was more productive is that humans would drive slower through the trees but it was safe to drive a little bit faster, and the autonomy would always drive 20% faster. So path planning and higher speed, being able to work day and night, a lot of those things provide value that customers really appreciated. Thank you.
Thinking machines at work in the world. This was the vision that we cast in the very early 80s, and it was encompassing of pretty much all the work we saw today. So this would be farming, mining, construction, automotive, and of course, in our world, space. And it encompassed the subjects of the talk, which included land, sea, air, underwater, underground, and by this time, space. And there wasn't a whisper of prospect for any fulfillment. The tech was absolutely not there. There was no sense that it would ever make its way into the world, given what it takes to break those barriers. Or the better way to say it is to make the grade. There aren't any real barriers, you just keep plowing through them. And of course, fast forward, and consistent with the topic of the session, there's industry in every one of them. Some fledgling, some fulfilled, and so much more to come. So I won't take us the whole way back, but we also had the inclination to work with industry from the get-go, in part because those alliances, without those alliances, it's a little slower, tougher for a university to creep up on it. And so by this time, 40 years ago, we were actually working with our first working machine in the nuclear accident meltdown at 3 Mile Island. And subject to Martial's morning question, what can a university do? See something that's worth doing, and something that industry couldn't possibly do, or that a government lab couldn't do, and chase it, get it done, and deliver. That came right out of our labs, and went to work for 4 years without a flaw, in full safety, well, not to linger, it didn't win any awards as a thinking machine. It was teleoperated. But candidly, the initiative to put these working machines in the world was never all that religious about what the technology would be to get there. It's, here's what's worth doing, and whatever it takes. So, of course, some things changed when this came rolling out behind the tree and across Shenley Park, and it was a new world. And it's just wonderful to be with everybody for a day, to look back at some of these origins and all the friendships it took to get us here. And, something to get in mining is that most of us sitting here wouldn't be aware of, is that all of our steel, all of our aluminum, all of our glass, every copper wire, all the electronics in our devices, all the lithium in our batteries, pretty much everything that people have or eat come from us with mining or farming. And I think it's a much lesser known story about the extent to which CMU's pioneering was incredibly operational, not just in causing these matters, but in cooking them up. And I'll say a word or two of them about that along the way. Oh, by the way, what we're looking at here was, I'm going to say this might have been 91. So it would have been before, I couldn't keep the date straight, but there were some beautiful demos yesterday with buses yesterday, and those were on order of like 96, 97. And consider it was like 5 years before that. And the other thing to get is that the commercial partner didn't think it up. We thought it up. We approached. We put the proposition out there and cast that vision that this is the one, this is your future. Of course, they'll always make better chassis, better engines, better paint job, better cabs. But this is the distinctive future. And we cooked it right here on campus, except, of course, for going to the proving grounds and living in the trailers and doing what it takes. And these are a dozen of those fundamental patents, fundamental in the sense that they are the foundation, and co-developed and then vectored to that partner. And at the time, their business team, which we were pretty friendly with by that time, of course, it was a closed meeting, but they viewed that those simple 12 patents were $1 billion of value, in the sense that they were foundational and upon which it could be built. I heard somebody said just within 2 days, told me that there are now over 10,000 patents by that company in the broad area of operational machines and digitization of mining and construction and other matters. Hard to believe, but good companies have a way of really doing it. Now, this seems like a jump and way out of it, and I think it's no secret. At one point, we had a good day, and also it's so interesting. Some of those. I'm looking at that one red shirt, and another old timer that seems to be in from the get-go, and part of everything was in there. But a lot of the companies that came out. My point in this has nothing to do with an eagle and a $2 million check. However, it does have to do with who's on the windshield. And I'm not diminishing who's on the other side of the truck, because what was missed by so many, and even most of the team may not have known it at the time, was that Caterpillar actually first found us, not through this racing, not through the trucking, but from some excavation back before 1986, when their technology scouts picked up on us digging, and the idea that automated digging might become a something. Anyway, what was this about? Well, the code base for this, again, it wasn't a big one. I'm going to say probably 500,000, 750,000 of C, lines of C. But it was a system. And I think that the real effect of this kind of thing was, of course, to transform belief. People have said that here. But also a leap of technology. And to ignite industries. So chatting about industry, this ignited industries. And that led to the project also referenced. And so the point of it with that particular sponsor was to evolve from that code base the system that would ultimately do what we're looking at here. And it's intriguing. Let's say, well, maybe a couple thousand. Actually, they're less than 2,000. But right now, while we're sitting here, just that little fleet of trucks is driving autonomously, and I'm not talking a little autonomously. I think most people picked up that is level 5, depending on how you look at it. But the distance that they're driving while we're sitting here is from the Earth to the moon. Another way of saying it is, oh, well, that's a couple of trucks going maybe 2 million miles a week. I think the more important thing is that, as people point out, they aren't little. And by the way, it's not little like that first one we did. That 777 might have been, I don't know. I do know. It's 226 tons. These are monstrous, and they carry north of 300 tons in load. Besides, as we talked about real industrialization, having to make the business case. And of course, that does mean you've got a tech. It does mean you can reduce it to practice. It does mean that you got a market, but it does mean you better make the numbers. So I realize not everybody is like miner. My family was a miner. We're miners. I worked construction a long time. And there's no secret to anybody that I moonlight on my Carnegie Mellon job by being a real deal farmer for, I don't know, 4 decades now. And I think in answer to Martial's great question this morning, what can a university do? See something worth doing before its time and make it happen. So maybe another way to say it is see the future and make that happen. Anyway, so a ton of ore, they're not all the same. Some of that footage was in iron, and that's cheap ore. That might go $150 a ton. So one truck is only $1/3 You get into copper, that could go, I've seen it $9,000 a ton. Times 300 tons, that's a lot of millions in one load. So I'm not saying they're all going to be like that, but more and more, those are evident. Now, This was a long time coming. By the time this was coming, I had adopted some of my own equipment. I run about 400 acres of hay. We get about 3 cuttings here, so at round numbers, that's 1,000 acres. And with narrow equipment, it takes about, narrow old hay-bine equipment, it takes about a mile to get an acre. So, you know, that's 1,000 miles at maybe, I don't know, 3-4 miles an hour when you're mowing with the old stuff. And my point here is you got to go day and night for days. And that's tough on top of the day job. Plenty of farmers do it. But consider what it was like to be masters of the trade that we had developed at that time, and see that there were these applications where almost was good enough, where you were out there dealing with traffic and all the safety, but I had to deal with safety because I wasn't there all the time. A lot of times I'd fire it up and come back to the city or go to Washington. And how I did that was I grazed cattle, and my fences around my big acres are electric. And those are pulsed, high voltage. So those are pulsed fields that are around those wires. And with a freshman, developed a little detector, which was proximity to the fence wire. That's another way of saying it. No matter what went wrong, it couldn't go off the reservation. Now, I did that a decade ahead of commercialization because what you know when you have this is that it takes a decade or more to get there. Companies don't just implement because they could, given all the process of liability, safety, other things that mattered. But candidly, I couldn't even have kept my farm except to be that kind of early adopter. Anyway, this was, in one proposal, we cast something that became known as the National Robotics Engineering Consortium. And candidly, that was to really bring into existence a structure for taking it the extra distance. And you could say consortium, you could say almost commercialization. At least those are the objectives. Now remember that we were selling, going directly into, I should have mentioned that when we were doing that very first nuclear work, you know, that in many ways changed the little group that was doing it, you know, to actually enjoy working with industry, big companies. Bechtel, which was whom we were commissioned by, was actually the largest AE construction outfit in the world. Just like the cat's the best, you know, the biggest at what they do, and Deere is the best at what they do. Biggest, I shouldn't say biggest. Now, this was, as part of that proposal, the key part of the proposal was there will be a technology that will transition into industry. And oh, by the way, we'll start a center. And so this very first one was easy to write and win, because, quite honestly, I was already doing it, right? And yeah, I think the movie either was too quick or didn't play, but that flatland would have been El Centro, California, where we mowed the first 100 acres, and that would be a consequence of that first project. So those were two of the patents that came of that. And, you know, in these things, I don't know that there is really a history. There's so many different versions of it, and you never know. I don't know that you ever know anything that was really done first anywhere, except, I guess, in the context of today. You know, CMU is the first for so many of the things we're looking at. But at least the patent office thinks so, and it's stronger than most papers. And you are now looking to one that lots of people never saw. So this is actually the first autonomous digging machine on planet Earth. In this case, we don't have the bucket on it, but that jet is actually supersonic. I should say before this, we had very early contracts in manipulation of diffuse media. So this podium is a discrete thing. The earliest desktop robots were taking red blocks and putting them on blue blocks, on white blocks, or putting rings on sticks of object, object, object. Diffuse media is a natural world. Diffuse media is dirt. It's sand. It's planetary surface. It's mining ore. A different world. And we did the science. And then this was an example where, I know you'd have to squint at the bottom, but there's actually a pipe. And we're doing it with the air because it's a leaking gas pipe. And if you hit steel on steel and making a spark in the gas, it causes explosion. And then the only reason I do the preliminary in the lab now, where we were using a vacuum to go after the pipe, is for a quick glimpse of the screen where it was stunning to get the forward and back solves sufficiently to implement the controls, and such that this thing is touching itself along, or if it bumps into something it's touching directionally, and strategizing on that. So there's a tremendous amount of proprioceptive work and force work in these machines, distinct from just driving around. Next step is pretty well known within our own sphere, maybe not as well in the outside world, stepping up in a big way. And, you know, I'd mentioned that particular company had been tracking us and had become good friends from way back in that first little excavation I showed. And when we first approached with the grand vision and got down to the table talk, well, what are we going to do? So we really had them. And we leaned back, and there were two propositions. I wanted to dig. They wanted to, well, we could dig and we could drive. And they could see it. So I personally wanted to dig. And their mining department said, let's drive. And I said, let's dig. And they said, let's drive. And they said, let's dig. And I said, let's drive. Or they said, let's drive. And I said, let's drive. And that's what led to those trucks. But this was big. And so a couple patents there, and here's how it's done today. Now, this is not exotic. This is just how it's done. Digital design that exists before the fact, the operations of the day embedded in the machine. It's common, like it is in the cars of the time, that there's an operator there, but so much different than having all of the things that operators used to do. About what operators used to do, this is a tough machine. This is one where I'm not very good on it. And I guarantee most people here would take 10, 15 years to get this good. And you can see, particularly in some of the angle shots and how it goes, how much you have to see in order to really get the result of the design you want. And so much of that and so much of these big dozers has evolved from the early work. So I guess I'm not going to take the long story to go through it, but just in terms of force, it's now automatic how you engage, how you fill a blade, how you carry that material a distance, and in the end, how you drop it off, how it auto lifts, tilts, and how it gets back to where you started. Now, operator in a cab usually, almost always, but the productivity, there's so many arguments for why it makes sense. I put this in for Marshall. I'm not even sure if he's still there. Yeah, well, here's the thing. It doesn't matter. I enjoy it. Yeah, there you go. And Larry's still here. So, there was a time when in that early going, and Larry showed some beautiful things in the can. So, and Chuck talked about step, stop, look, think, step, stop, all that stuff. So the Holy Grail was continuous motion of these planetary things, because the reason, a lot of them have a mechanical speed, maybe 5 centimeters a second, but their actual progress in terms of map speed is this, because they're not in motion very, thing. So this would have been like 90, I'm going to say 92, something like that, where, self-contained, continuous, obviously not hardened for space, but in that context. And then that has become that just then became basis for things like a robot that's on the far side. All that, it's not that became that. So much of the fundamentals presented yesterday became basis for how these planetary rovers of today and for all time are going to operate. I didn't put in there a version of our own next one. I almost shed a tear when there was a Clint Kelly thing yesterday, and Clint mentioned this significant pursuit of lunar polar ice. So the idea is that many view it to be the most valued resource in the solar system, because you can, of course, melt it and drink it. You can grow food with it. You can extract the oxygen to breathe it. You can put it back together to make rocket fuel. And our next rover, our next moon rover, we'll explore it to characterize it. So I didn't put it in here, but. So about the physical forms, the guys that paint it green have green ones. The guys that paint it red have green ones, or red ones, and the guys that paint it yellow have yellow ones. But There's a lot of this. And candidly, the cabs, you know, they got a lot of glass, they have air conditioning, they have pedals, linkages, steering wheels, stereo, a lot of things we don't need, or that automation doesn't need so much. The name of the game in mining is dollars per ton mile. Carry as much as you can. These in trucking, new forms for the future. Yeah, who knows? Given what we've seen over the first 4 decades, it's always challenging to predict. So, it's actually a pretty good run of it in these arenas that are other than cars and automotive that we, in addition to our own vision was actually encompassing. And many people talked about how cross-cutting a lot of these things are. And I couldn't believe how many people stood up here and said field robotics, including our current department head. It's certainly in for the duration and has and will continue to dent the world. Everybody mattered. And that really sunk in here over the day or two. Industry means industry. And I personally always enjoyed the commercial partners for their capacities and what they could bring to the game as complement. Innumerable spin-offs from ourselves. Sponsors, of course. But I think you get the idea. It's not just, here's DARPA, here's NSF, here's DOT. A lot of sponsors that have mattered are the ones that are out there in the world. And of course, RI and CMU. And I don't know, maybe this whole thing could have happened somewhere else. It's moot because it didn't happen right here. And I actually think sometimes if we had started 5 years earlier, it might have fizzled. I think if we started 5 years later, somebody else would have done it and run right over us. Anyway, great to be with everyone. Thanks for the excessive time and the indulgence.